William is the presenter today. He's the product manager for drives and sensing. So he's got many years of experience with the company. He's one of the boffins within the company when it comes to automation. So he gets the Einstein Award on a regular basis for warping all of our minds with what he can and can't do. Yeah, just if everybody can see, there's a chat function and there's a Q&A function. Please feel free to drop any questions in. I will keep a note of them, and if pertinent, ask during the presentation. Otherwise, I'll hold them back until the end of the presentation. And we look forward to a very interactive session with everybody. Any questions during the presentation, please just pop it in on the chat and I'll assist where I can. Thank you. Over to William.
Wow, Conrad, thank you for that introduction. I'll have to repay the favor in the future. Welcome, ladies and gentlemen. Thank you for joining us. Rather excited to do our first webinar. So let's get going. So today's goal is to help you, the salesman, have a deeper understanding of what a variable speed drive is and some relevant functions relating to variable speed drives. There's a basic contents we'll be following. Motor starting, motor basics. We'll look at some drive part numbers, the differences between single and three-phase drives. We'll have a special focus on pump and fan drives, and then look at some applications as well thereafter. We're going to see how we're going. I'm hoping an hour tops. So if we're making good time, we will skip the interval. But if there's a lot of interaction, a lot of questions, we might just take the 5-minute interval in between. If you can, ladies and gents, please keep your catalogs on hand, the new 2020 catalog. There will be some slides where I ask you to go to a specific page to give us a deeper reference. All right, let's go. So let's start with some motor basics, so we're on the same point. As you can see by the animation, a motor, the shaft speed is influenced by the rotating electrical field. So as the electrical field rotates around the stator of the motor, the rotor inside, or the shaft, is pulled towards either end. For a two-pole motor, as we have in this example, you can see by a simple calculation that at 50 Hertz, you would have a speed of 3,000 RPM. If you had to double the amount of poles, excuse me, in the stator, squeezing in twice the amount of coils, obviously you would halve the speed, as the field will take twice as long to go around the motor, and the motor would be half. Similarly, with an 8-pole motor, you will be down to 750 RPM, around there. So the important thing to understand is, in this formula, is that the motor speed is linked to frequency. And we're going to explore that a little bit later as well. So contactors versus variable speed drives, or direct online starting versus variable frequency drives. You can tell by the size of the boxing gloves on the drive which one is my preferred solution. I try not to have a bias, but it's quite difficult. So we're going to have a look at the differences, some pros and cons between the two starting methods, and it'll hopefully give you some more information. So firstly, let's look at a direct online starter. You can see on the right-hand side, we have the power circuit as well as a control circuit. This is a typical power and a typical control circuit. You can't get much simpler than this. So let's have a quick look at this video and how the mechanical forces are on the motor when it started direct online. You can see when the motor changes speed from rest to full speed that there is quite a heavy impact on the motor. And you can imagine if anything is connected to that output shaft of that motor, it obviously is going to feel that same impact. For this reason, direct online starting is relatively rough on equipment and maintenance heavy. You can see by the power circuit that you would require a D-curve breaker, contactor, as well as an overload. Let's have a look at what's actually happening in terms of current drawn when the motor starts. So you can see from rest position, where the contactor switch is on, to 50 hertz or 3000 RPM for a 2-pole motor, that happens in less than 1 second, probably less than 0.1 second in most cases. And you can see at that point in time that the amps shoot through the roof. So obviously this is your 7 to 10 times starting current that a contactor would experience when turning on a motor direct online. And you can see how that's related to the violent video we just saw earlier when the direct online motor was starting. Let's have a closer look at variable frequency drives and how they operate and how they control the motor speed. So a quick look at the power circuit of the drive. So just like the contactor, we've got incoming 3-phase 400 volt. However, this 3-phase AC voltage is converted into DC voltage inside the drive's DC bus. This energy is stored in capacitors inside the drive and then switched through the drive's output inverter, or IGBTs as they're referred to. These little switches will switch extremely fast in a special pattern, which will then simulate a sine wave. So the length that the switch stays on for, or the time that the switch stays on for, and switches off, that duty cycle of that on and off time is referred to as pulse width modulation. So the longer the switch stays on for would be the higher the voltage would be generated. You can see by this little schematic here, that is how the drive controls the speed of the motor. So if the motor was running at 10 hertz, the drive would be switching around 700 hertz, 700 times per second. It'll be switching its little IGBTs to simulate a 10 hertz wave. At 20 hertz, the drive will be switching a lot faster to simulate a 20 hertz wave. And as you go up in the motor speed, obviously the frequency that the drive switches at also needs to increase. So the drive simulates an AC sine. It is not a pure AC sine that comes out of the drive, but a simulated AC sine wave, referred to as pulse width modulation. So let's have a look in comparisons to how the drive can start a motor from standstill to running speed. Oops, sorry.
Button. The default speed reference is 60 hertz.
The drive would take 10 seconds to ramp up to 50 or 60 hertz in this case. It's at full speed. And by default, an additional 10 seconds to come to a standstill. You can see there's no impact torque whatsoever on the motor when it starts. The drive can control the starting current because it can control the frequency and it can control the voltage that's coming out of the drive. Also, you can see that the control circuit and the power circuit is a lot simpler than that of a direct online starter. You only need one control switch to give the drive its run signal, and 3-phase in and 3-phase out. All the built-in protection is inside the drive: phase failure, phase reversal, overload. So it does make your power and control wiring a little bit faster as well. Also important to note that because of the soft starting of the drive on the motor, is that you do not need a D-curve breaker on the input of the drive. A conventional C-curve is good enough, as the breaker doesn't experience the inrush as it would in a D.O.L start. So let's have a look at the startup of current versus time. You can obviously see when the drive starts, it controls the frequency up until 50 Hertz. And because it controls the ramp of frequency, it controls the motor current that the motor would draw as well. The ramp time on a drive can be set anywhere from 0.1 seconds to actually 6,000 seconds if needed. So this gives you a great amount of control and soft starting ability on the drive. Contrary to popular belief, a drive is a much better soft starter than a soft starter. In fact, it is 10 times better than a soft starter. Let's just have a quick look at some pros and some cons of drives and contactors, just to be fair. So drives pros are plentiful. We'll just mention a few. Obviously, you have full motor control, full motor protection, phase failure, phase reversal built in. There's energy saving, which we'll touch on a little bit later as well. Less mechanical wear on your conveyors or your pumps because of the soft starting capability. It gives you a lot more programming flexibility, which prevents you from making wiring changes. You can rather just make programming changes. Improve power factor and a lot more. Some of the cons on a drive, yes, it's obviously going to cost a little bit more than a contactor initially. It does generate heat as it has semiconductors that switch very fast. That heat needs to be dissipated, normally through panel fans and ventilation. It does have a larger footprint than a contactor, and those are about all the cons that I can come up with. So the contactor is obviously no heat, is a low level installation, is a low initial cost, and it's relatively small compared to a drive. So those are the good things on a contactor. If we look at the cons, there's no programming flexibility in the motors fixed, and the most devastating is the mechanical wear that can exist on the output shaft. Obviously, there are applications where you do not require a drive, like your pool pump, for instance, but there are many applications where a drive would benefit. Let's have a look at our range of VFDs. Selecting the correct drive for an application is very important, as if you don't, you could be quoting a higher cost than you actually need, or even worse, the customer could order a drive and have a bad user experience. Maybe the drive is not suited to the application and it lacks maybe certain functions or features. So we are going to spend some time on looking at what exactly, what drive to use for what application. So a brief overview, we've got the ME300, which is our new to the product family. It's a ultra compact, economically priced variable speed drive, from 0.2 kilowatt to 7.5 kilowatt. We've got the MS, which is similar to the ME, except it's got a lot of smart built-in features like built-in PLC, built-in EMI filters, removable keypad, and also some field bus options. We also have the CP, which is our pump-specific drive, and the C2000, which is suited to more heavy-duty applications like cranes or hoists or crushers. The elevator drive is obviously only suited to elevators, and our faithful E drive is a good all-round drive for general applications up to 22 kilowatt. Let's have a look at the part number breakdowns on some of our drives. So let's go to page A20, as you can see in the top right-hand corner. So some of our drives have different part number breakdowns or naming rules. So it's important to understand this. So when looking at the part number, we can quickly assess what exactly it is and if it's correct or not. So the E series drive, you can see that the part number or the kilowatt of the drive is embedded inside the part number. So 007 would mean 0.75, or 015 would mean a 1.5. On the end of the part number, it would end in a 21 or perhaps a 43. If the part number ends in 21A, it's a 220 volt input single phase. 220 volt single phase. That's where the 21 comes from. If the part number ends in a 43, that means it's 400 volt three-phase input. Okay, that's our VFD-E part number breakdown. Our newer drive range has a slightly different naming rule to the E series and the rest of the ranges. In the MS and the ME drive, instead of the kilowatts being embedded in the part number, Delta have decided to embed the actual rated current of the drive. So for instance, on a 400, let's go with this example here, on a 750 watt VFD, a VFD-488ME21ANN, that's the 750 watt ME drive near the top. That has a rated current of 4.8 amps or 4A8 amps. Similarly, the 1.5 kilowatt drive would have a rated current of 7A5 amps or 7.5 amps. So it's quite handy at a quick glance to look at the part number and know exactly what the rated current of that drive is. It is a slightly different naming rule to the rest of the drives, and I think this is probably the naming rule Delta will continue on their newer ranges of VFDs that will launch in the future. Similar to the E series, the part number that houses a 21 near the end would be 220 volt single phase input. And the part number that houses the 43 near the end would be, again, 400 volt three-phase input. Very important to note that that symbol represents input voltage, not output voltage, but input voltage. The C drive is very similar to the E. Again, the kilowatt is now expressed inside the part number. So this is page 21. And again, 43 to describe 400 volt three-phase. In the C series, you'll notice we also have a 575 volt version as well as a 690 volt three-phase version for the mining industry. Those part numbers would end in a 53 or a 63. The CP is much the same, except it obviously has CP in the part number and ends in 21. It has IP21 capabilities off the shelf. So I mentioned earlier that the part number was looking at the input voltage, the supply voltage to the VFD. This is very important. That is a very common question that we get. Do you have a single phase drive? And now that's a very open-ended question. The answer is yes, and the answer is no. We have a single phase input drive, but the output is three-phase 220 volts, as you can see in this diagram. So yes, the drive can take single phase input, as the code explains here, 21A, but the output is 3-phase 220. On the 400 volt 3-phase drives, it's 400 volt input 3-phase and 400 volt output 3-phase. So typically on a motor, on a small drive or small motor that's single phase supplied, your motor typically would be wired in delta 220 volt 3-phase and not star. So just to recap, we sell single phase input drives. Our drives cannot operate a single phase motor. We're going to have a closer look at our pump and fan drives, namely the CP and CFP series. Pump drives are big business, and a lot of applications are based around pumps and fans. So I just felt it was necessary to elaborate a little bit more about our pump-specific drives. If a customer is looking for a drive for a pump, centrifugal pump, or a fan, then these drives are suggested to be the best to offer. So a simple table here, we've got the ME drive, which is our economical drive. It is a pump particular drive, but obviously only up to 7.5 kilowatt. That's the maximum we can go on the ME range. Its bigger brother, the MS300, is also a pump specific drive, and it can go up to 22 kilowatt. The VFD-E can be used on a pump, but it is low on pump specific functions. What I mean by that is that some pump drives have special, obviously, pump functions embedded that will protect the pump or add value to an application, for instance. And the E drive is it's low on pump particular applications. So depending on the application, it's probably not the best drive to offer. Our CP2000 is a pump specific drive designed purely for pumps. We obviously don't have a 220 volt 3-phase version in CP, but from 1.5 kilowatt all the way to 280 kilowatt, CP is a really good drive to offer your client for a pump application. Then we've got one of the new kids on the block, the CFP2000. Now this is a CP2000 drive, except it is in a IP55 housing. And that drive only goes up to 90 kilowatt. So perfect drive for pumps or HVAC applications, limited to 90 kilowatt. Then we've got our C2000. Again, no option for 3-phase output. And if you're going to offer the C2000 for a pump application, it's complete overkill. The C2000 has too many features, and you'll be priced out if you offer a C2000 for a pumping application. It obviously can work. It'll work very well with a pump. It's just going to be 20% to 25% more expensive than, say, a CP equivalent. And obviously the last ED drive is our elevator specific drive. It costs a lot because of the safety features built in, and it's also very low on pump parameters because it's not designed for a pump. So I hope this table gives you a little bit of a better overview and what we can offer the client when it comes to pump drives. ME and MS are great for your smaller pumps and for low cost options, and your CP for your middle to high end to high kilowatt pumps. So we're going to highlight those two drives, the CP and the CFP. They are purposely designed for centrifugal loads, which is your pump and your fan type loads, suitable for rough environments. It's got a lot of embedded pump features. You can operate more than just one pump from a drive like this. Built-in PLCs, so you can formulate your own controls if you like. The CP2000, as I mentioned, IP20, and the CFP 2000 is IP55. So that's the new one in our catalog, the CFP 2000 IP55. You can see that on page A23. So the CFP, if I can highlight a little bit more on this one, it comes in two variations, one with an isolator on the drive and one without an isolator. We have decided to stock the ones without isolators due to demand. However, we do have a few isolator pieces in stock, and we obviously can bring it in if needed. This drive is very well suited to HVAC applications. It's got a very low electrical noise. It's got built-in chokes, built-in filters, and it conforms to a very high EMC standard compared to the other drives we offer. So the likelihood of this interfering with other telemetry in a building is very low. Hence, it's very well suited to HVAC applications. It can also be mounted on a wall. Doesn't need to go inside a panel because it's IP55. So it does make the installation a little bit easier as well. It's got a very high corrosive resistant coating on the boards. Conforms to the highest standard drive we have in our catalog in forms of the corrosive resistant coating. So very good drive for sewage plants or for water treatment facilities, anything like that where there's corrosive gases in the air. This drive would be very well suited to those environments. Everyone always talks about drives saving you money. Yes, it is true. They can save you money. And I just want to highlight the scenarios quickly and why and when they can save you money. So let's have a quick look at that. When it comes to pumps and fans or centrifugal loads, they have a particular energy saving capability, which is explained by the affinity laws, which I'll try and explain best I can. So the affinity law states that the water flow coming out of a pump or the airflow coming out of a fan is directly proportional to the speed. You increase the speed, the flow increases. You decrease the speed, the flow decreases. The pressure that that pump produces is proportional to the square of the speed. So the pressure is proportional to the square of the speed. Thirdly, the power is then proportional to the cube of the speed. Okay, so with this in mind, if we have a small percentage reduction, say a 20% reduction in speed, the 20% reduction in speed because of the cube curve law can result in a 50% energy reduction. So a very, very small reduction in your speed of your pump can result in a relatively large energy saving that you can get out of the system. Obviously, this is application based. You won't save a lot of money on every single application, but the applications where you can vary the speed of the pump during the day or during specific processes is exactly where you would save a lot of money. So just looking at the pump curve as it was. So the pump curve would obviously, as flow increases, power would increase as well in that cube law as we explained. You can see that a drive's curve will follow the pump's curve very closely, as because the drive can vary the speed of the pump and utilize that pump curve. If a throttling valve was used in a normal direct on-line application, you can see that power's minimal you could draw is about 70% of your load. So with this in mind, you can see that if you can vary the pump speed below 100%, there is a huge energy saving area that you can tap into. if obviously your pump runs at 50 hertz all day, every single day, which is the peak of this curve over here, you will not save the energy that the affinity law explains. You will, however, save a little bit in power factor. You'll maybe save obviously in maintenance due to soft starting, but you won't be saving in this energy area as explained by the laws. So just the last graphic to explain that is your power input is equal to your duty required or your output power required. That's what the VSD brings to the table. If you need 2 horsepower or 2 kilowatt, it can supply 2 kilowatt. However, on the D.O.L side, or the contactor side of pump operation, your input power is pretty much constant compared to what is required on the duty side. So varying that control valve to change pressures doesn't save you that much money compared to varying the speed of the drive and of the pump. I think we can work through the break. We're making good time, so I think we can carry on. If there's any questions, Conrad, now may be a good time.
We're good for now, William. You can continue. Cool,
thanks. So in order to help us upsell when we're in discussion with clients, we're going to be looking at a couple of applications regarding drives and some peripheral equipment. Namely pressure transducers, level sensors, and flow switches. So the pressure transducers and all the sensors that can connect to the drive connect in what they call a control loop, where the information is constantly fed back to the drive. The drive can take the information and make a decision on, do I speed up or do I speed down? This consistently happens as the drive reads the information from the field and creates an output on the pump. So let's have a quick closer look at our pressure transducers on page K23. If I wanted to have a system that keeps a constant pressure in a pipeline, I would need to measure the pressure and feed that pressure back to the variable speed drive. And I would use one of these pressure transducers to do that. So page K23 has our range of Huber pressure transducers. You can see the 5 to 8 is your general type, suitable for most applications. The 5 to 5 is a very low pressure sensor, special applications. The 520 is very similar to the 5 to 8, except it comes with a high burst demand. So this transducer is able to take 3 times full scale pressure before it fails. The 548, very similar to the 528 in its construction, besides the fact that it has a digital interface and some programmable outputs as well. The 540, the same, programmable digital outputs with an LED interface as well. And the 540 features the same high burst protection as the 520 has. So you can see by the small diagram that the transducer would retransmit 4 to 20 milliamps based on the pressure range that you select. So if I choose a 10 bar transducer, the pressure transducer will send me 20 milliamps at 10 bar of pressure. And obviously with a 60 bar unit, I would get 20 milliamps at 60 bar of pressure. That's how the drive knows what pressure is in the pipeline currently. So with that in mind, we're going to have a look at the control loop that actually happens and how the drive can maintain pressure. So this is a mathematical representation of what's going on inside the drive. We don't really have to worry about that, as the drive takes care of it for us. The pump is our output, and we measure the pressure and feed that pressure back into the drive. The drive then rotates the pump at a slower or a faster speed, and we read the pressure again and feed that back into the drive. Hence, you can see why it's called a control loop, as the pressure transducer continuously feeds back the pressure to the drive, so the drive can make changes according to the set point. So the set point is where I want to be. I want to be at 2 bar. I'm only at 1 bar. Please increase the speed of the pump. Once the pump gets closer and closer to 2 bar, the drive will gradually start playing with the pump speed to maintain that 2 bar of pressure. So this is a closed loop control for constant pressure. So let's have a look at where we would use this quickly. If I had a farm with 3 subplots on it, one plot's got 100 apple trees, the next plot with 500 apple trees, and the third plot has 1,000 apple trees. All the trees need to be watered at 2 bar of pressure, which is our hypothetical set point over here. So if I have my taps open only to 100 trees, my pump obviously only needs to be at, say, 1/3 of its capacity. So I can be at a relatively low speed, drawing low power from the system and maintaining the 2 bars that the trees, that the irrigation requires to give enough water. If I opened up a tap and started to water 500 apple trees, the transducer would register the drop in pressure. The drive would then speed up to compensate, and I would maintain 2 bars once again. And again, 1,000 apple trees, the drive would sense the pressure drop and ramp up to maintain speed again. So that's constant pressure with a varying demand of water. Another application where constant pressure could be used is to compensate for elevation. So if I have 3 plots again, each of the plots have 100 apple trees on it, but 2 of the plots are elevated above the first one. By compensating for the set point, I can compensate for elevation. We know that 10 meters of water level is 1 bar of pressure. So for me to pump water 10 meters high, I need to exert 1 bar of pressure. So my set point, number 1, which is 2 bar, I can water 100 apple trees at sea point, no problem. At sea level, not sea point, my mistake. If I then need to go 30 meters above that, all I need to do is add 3 bars of pressure onto the existing set point. So that'll be 5 bars in total. If I need to go 50 meters above sea point, then I would need to add 5 bars of pressure onto the initial set point. So you can see that constant pressure is quite handy, and not in terms of energy saving, but also for a process to happen evenly. Let's have a look at another closed loop scenario, this time with level control. So we're going to sideline our pressure control for now, and we're going to look at a closed loop scenario for level control. So if we go to page K24, near the bottom, we have 2 types of pressure level sensing transducers, also referred to as hydrostatic level transducers. The reason why they're referred to as hydrostatic is because these transducers, the 712 and 713, measure the pressure exerted by the water above them, which is where the word hydrostatic comes from. So the transducers will be placed at the bottom of the tank or at the bottom of the borehole, and they would measure the pressure exerted above it. We remember from the previous slide that 10 meters of water would exert 1 bar of pressure. So for instance, the little JoJo tank I've got here, 10 meter high, it's not that little, it's quite a big one. for a 10-meter high Jojo tank, if I want to measure 10 meters of water level, I would need a 1-bar transducer. So that can measure 10 meters of level. And you can see that the cable that comes with that transducer is a 15-meter cable. Obviously, we need a little bit of extra 5 meters at the top here so we can terminate and wire it into our drive. On the borehole side, here you can see we've got a 100-meter water column. So I would need to go with a 713 transducer. 100 meters would exert 10 bars of pressure. So my transducer needs to be a 10-bar unit. And you can see that my cable length is 125 meters. So that gives me an extra 25 meters above the borehole where I can run a wire to the electrical panel or terminate just above ground. The level sensors have a very special type of cable. Embedded inside this cable that runs the length, that connects to the transducer and runs to the top above ground, is inside that cable is a very small air pipe. You can see it over here in this termination box. So what this little air pipe does, it measures the atmospheric pressure above ground and compares that to the pressure exerted by the water in the borehole. And with that difference in pressure, the transducer can work out what signal to send back. This is it's a nice feature because the transducer does need to be calibrated. It always has a reference to atmospheric, so it does help with its long-term stability. Obviously, it doesn't help because it doesn't help in a certain fact because it's a special cable used by the transducer, and as you can note by the price, the longer the length of cable, the price starts to climb quite steep. So the price that you see in the book, particularly in the 713s being so high, it's not because of the actual transducer, is because of the actual cable that comes with the transducer. And remember, this cable has to be sealed perfectly inside the transducer, and it comes coiled up as an 80, 100, or 175 meter cable that you buy with the transducer. So just some explanation regarding the price you might see in the book. It's largely based on the length of cable.
Sorry, William, just a question.
Yeah.
What would happen if you were using a 10-bar transducer, but you were dropping it further than 100 meters? You dropped it to 120 meters.
Good question. The 712s and 713s have double overscale protection. So I could drop a 10-bar transducer in 199 meter depth water, and it shouldn't fail. I could only read 0 to 100 meters, so I won't be able to read the last 100 meters, but the overscale protection on these transducers is twice the full scale load. So you can times by 2 the actual rupture pressure, as they call it, where the transducer would fail. Hope that answers the question.
Thank you.
So it's twice the rated depth or twice the rated pressure is what the transducers can handle. Good question. Often, if a guy has a 150 meter hole, you don't always want to measure all 150 meters. Sometimes the water level is only maybe 100 or 80 meters deep, but the hole is 150 meters deep. So just something to keep in mind when and if you talk to the clients about these products. Again, we got our PID loop diagram here. Obviously, except for this time, we've exchanged the pressure transducer for a level transducer. So in this case, the drive gets the level back, and depending on if it's emptying or filling a tank, we would configure the drive in what they call negative or positive feedback. So the drive has it built in. I just select a parameter, you filling or you emptying, and the drive will control the level of the tank. as such. So just to paint that out into a picture, in scenario 1, our set point is near the center of the tank, as you can see. If the function is set to emptying in scenario 1, then the motor will not start because our water level is well below our set point where I want to empty to. So my pump will not start at this point in time. It'll wait for the tank to fill up, maybe to a predetermined point, and then it'll only start to empty the tank and try and maintain this set point. Obviously, vice versa, if this scenario 1 was set to filling, it would start immediately and attempt to fill the tank and maintain this level. Scenario 2 is pretty much just the opposite. If I'm sent to emptying in this scenario, it would start immediately and attempt to empty. Important to note that the bigger the difference between the set point and the current measurement, the faster the drive will try and act to maintain the set point. If the level gets closer to the set point, the drive and vice versa would slow down. And by doing this, if the pump system is designed correctly, the drive and the pump and the level transducer will maintain perfect level in a given tank. Obviously, if the pump is big enough to get rid of or to pump in the amount of water that's being used, that's up to someone else to design. But the drive and the transducer will maintain perfect height in that tank. The great thing about using the transducers and the drives and going the analog route like this is that you can easily set start points, stop points, change your set point, where you want to maintain the level. It's very easy to achieve by changing a couple of parameters in the drive. You don't have to climb into the tank and change float positions and change probes or anything like that. It's an infinite amount of set points and an infinite amount of start or stop positions that can be programmed. Just having a look at other modes of level control. Obviously, not to forget the float switch. That's on our page K35. Obviously, the float switch is the economical way of keeping a level in a tank. The differential is set internally by the angle of the float switch. In this example, it's a 30-degree or 60-degree difference would turn on and off. So that would be the height that you basically can control at. You can add multiple float switches together to have a high, a low, or a middle level. However, it is hard to know the exact level of the tank when using float switches. However, they do have their part in applications. Another type of analog signal similar to the level transducer would be an ultrasonic sensor. If you look on page K9. You might have noticed that we've increased the range of ultrasonic sensors by quite a lot. Up to 8 meters sensing distance is now available. So the ultrasonic uses a slightly different, or not slightly, quite largely different to the level sensing. It uses the time of flight of ultrasonic sound waves reflecting off the water surface and being detected back by the sensor. So the time it takes for the sound waves to be transmitted, to be reflected, and to be received again, that is how the sensor determines the level of the tank. Some cons for the ultrasonic sensor is that it needs to be set up, it needs to be taught. So in other words, to teach the sensor where empty is and where full is, so it knows the level, you need to empty the tank and you need to fill the tank, and then teach it at each point so that it knows the difference in time of sound waves. So this obviously can have some issues in commissioning. It might not be practical to empty or to fill a tank where you use the 712 or the 713, because we know water exerts X amount of pressure and it's constant. There's no setup needed. You can just drop the probe in the bottom of the tank and it is calibrated. However, the ultrasonic is preferred for a non-contact level control. If you're measuring in a sewer or in dirty environments where there's maybe the liquid contains certain amounts of solids, you don't want to be using a 712 or 713 level sensor. That being said, the 713 is designed for groundwater, but for things like sewerage, you wouldn't want to put the probe in there, it will fail. So non-contact ultrasonic sensor preferred for things like sewerage measurement. Having a look at pressure transducers again, this time air pressure, on page K25, we have our 699 differential pressure transducer. So the differential means it measures the air pressure between 2 points. So point P1 and point P2, or pressure P1 and pressure P2. The transducer will measure the difference and then send that difference out as a signal, 4 to 20 or 0 to 10 volt. The scale that we use for these transducers is millibar. Please note that these 699s have 3 pressure ranges, which is selectable via dip switches inside the unit. So if I take the first unit on page K25, for example, it can be set to 0.3 or 0.5 or 1 millibar differential measurement. This has to be done on dip switches on the unit. Where would you use it in an application? Very quickly, in a building or in a stairwell of a building, you would typically have a pipe in the stairwell, P2, and another pressure point measurement, P1, in the general corridors of the building. So what the transducer would do is measure the pressure difference in the corridors compared to the stairwell or the fire exits. In the event of a fire, you want to keep a positive pressure inside the stairwell at all times. So when there's a fire, the drive will get a signal to start, and it would try and maintain a positive pressure inside the stairwell to keep the staircase smoke-free and fire-free. Also, a note on that, the CP and the MS300 pump purpose drives have built-in fire mode features. So if there is a fire, the building management system can send the signal to the drive, a fire signal, and the drive can operate in what they call fire mode, where it will not trip on any small or any alarms, basically. It will run until complete destruction. So if a fire is busy burning, the drive's not going to worry about it being a little bit hot, and it's not going to trip on over temperature. It'll carry on running until it can't anymore. So that's another nice feature for the building automation guys. Is the fire mode capabilities of our CP and CFP 2000s. Let's have a look at the Annexure 11 now, in the back of the catalog. This is a new chart that's been added, explaining the dual duty ratings of the ME and the MS drive. I'm going to spend a little bit of time on what this means and how you can exploit and upsell because of this. So the ME and the MS variable speed drives have dual duty rating, which means the same drive has 2 different, let's say, capabilities. As you can see in the example here, a 750 watt drive can be used for a hoist system, or the same drive can be used if you change the duty, the setting, in a 1.1 kilowatt pump. A hoist is obviously a lot heavier in terms of starting currents, stopping. It's a stop operation. It takes a lot of impact to get it going. And that's why it has a lower kilowatt rating. However, on a pump side, when a pump starts, it's a nice and smooth start. It doesn't get a lot of interference from external. It can run at a fairly constant load. So the drive manufacturers are able to program in different duty ratings for different applications. And we're going to highlight some of these going forward. You can see from the table, for instance, a 2.2 kilowatt drive, heavy duty by default, can be a 3 kilowatt drive in normal duty. So again, a 2.2 kilowatt conveyor or a crusher, that same drive can operate a 3 kilowatt pump. Here we've got a little chart explaining the differences between the heavy duty and the normal duty ratings. So in heavy duty, we have a much higher starting current capability. So we can go up to 200% starting current for 3 seconds. However, the nominal rated current of a heavy duty drive is lower than that of the normal duty. So it has a higher current to start maybe a compressor or a hoist, but the nominal operating current is lower than that of a normal duty drive. So you can see on the pump system has a slightly lower starting torque capability, but a much higher nominal current. So a pump, again, for instance, or a fan doesn't require a lot of energy to get it going. It's in fact a very smooth and soft start. So normal duty operation for a fan is perfect. These are all the drives in our catalog that have dual duty ratings. The MS E drive doesn't have. CP, CFP have dual duty. The C 2000 and the ED does not. But I'm going to particularly highlight the ME and the MS for the following reasons. The default duty of the MS and the ME drive is heavy duty. So you can see VFD-13AME43 is 13 amp, heavy duty rated. The same drive can be set to normal duty and the rated current would be 15.7. So for instance, what I'm trying to highlight is if a customer had a pump which was rated for 15.6 amps and you had a quick look at the VFD-13AM, obviously it's not enough current, 13 amp. However, setting that same drive into normal duty, which is a pump duty, would utilize 15.7 amps then from the drive. And it would be enough to supply to the customer the VFD-13AME and not have to go to a higher frame size, which obviously would cost more. I've encountered quite a few scenarios already internally with our salespeople, even with our technical staff, where the customer will send a request for quote, and it's exactly the case. The drive selected was too big, and we could have selected a lower drive, changed the duty, and saved the customer a couple of thousand rand, and obviously have more chance of winning the sale. This is why I'm highlighting the fact that the ME and the MS have a heavy duty by default, and you can increase the capacity for a pump if it's set to normal duty. So on the alternative duty on a particular drive, the MS and the ME is the only drive that would increase its nominal current capacity by changing the duty to the alternate duty because its default is heavy. Any other drive, if you change to the alternate duty, it's a higher duty rating, which means your current is lowered. Your nominal current is lowered. Something to remember. We're going to stick with Annexure 11 now and look at the derating chart for our 5 to 5 volt drives. So this would apply more to the customers, obviously, who service the mining areas. As you might know, we have a range of high voltage drives, 5 to 5 rated drives. But what the table explains is the fact that our drives are not designed or rated at 525 volts. Some of them are designed or rated at 575, and some of them are rated at 690 volts. The nominal input voltage range will still be, can still handle 525 volts. But the important thing is that the drive's kilowatt explanation is based on a voltage at something higher than 525 volts. So you need to derate when you are quoting on a 525 volt application. For instance, a 30 kilowatt C drive, it can, in light duty, it can do 39 kilowatt and 690 volt, but it can only do 30 kilowatt in 5 to 5 volt. Another example, a 90 kilowatt C drive can do 114 kilowatts if the supply voltage was 690 volt. It can only do 87 kilowatt if the supply voltage is 5 to 5 volt. Okay, because the current is, the rated current is the rated current of the drive, that cannot change. Because of voltage fluctuations, we would obviously have kilowatt fluctuations. So the safest bet if you're quoting on a 5 to 5 volt system is to ask the client for the rated current of the drive, of the motor, apologies. If the rated current of the motor is 85 amps, then you know that an 86 amp drive will work. So that is the safest bet, is to get the rated current of the motor and compare it directly to the drive's rated current. That's the best way to specify a drive for 5 to 5 volt applications. Bearing in mind, again, that our drives are not rated at 5 to 5, but are rated at 575 and 690 volt. Okay. Hope that's not too confusing. Back to page A19. We're going to just highlight the ME drive, being one of the newer drives to the catalog. All of you should have remembered the predecessor, the VFD-E. So the ME has replaced it, has been the case since the beginning of the year. The ME has a host of benefits versus its old EL predecessor. Number one is the size. The drive is much smaller in size, up to 60% reduction compared to the EL. So with a small footprint, we will surely, and we have already, won more market share just because of the footprint of the drive. The EL was a little bit larger than some of the competition previously. However, now with the ME in stock, we can compete directly. Just again, the voltage, 400 volt size differences. All right, we're nearing the end. Thank you all. I just wanted to highlight the summary of our drive offering. So again, the ME300 is our compact economical drive. Maximum power, 7.5 kilowatt. There's no fancy features, no field bus, no internal PLC, no add-on I/O. The MS300 is similar in dimensions to the ME, but obviously comes with a host of extra features like field bus and internal PLC and removable keypad, etc. CP2000 is a pump-specific drive, up to 280 kilowatt. With built-in PLC, you can add on I/O and with field bus options. CFP 2000, maximum 90 kilowatt. Very similar to CP, except it is IP55 It has a better noise capability compared to the CP and is ideally suited to HVAC applications. The C2000 is basically the trump card, full of features, can do just about any application, and we can go up to 560 kilowatt in 400 volt. And lastly, but not least, is our ED drive, which is very specific for elevator applications only. Thank you all.
Thank you, William.
Thanks, Conrad.
Couple of questions.
Sure.
Can you install the drives side by side?
Yes, all drives can be installed side by side. There is a slight derating that needs to be applied. For instance, I'm going to talk in general terms, so it might differ from drive model to drive model. If a drive is rated for 60 degrees ambient operating temperature, if it's mounted side by side, that rating sometimes drops by about 10 degrees, so maybe 50 degrees operating temperature. So if you are going to side-by-side mount, yes, it's possible. The ME is a great drive to do side-by-side mounting. However, there is a small derating in the ambient temperature that it can operate in if you are side-by-side mounting.
Okay. Do I need to use a surge arrestor to protect the drive?
It's always a good option. Surge arrestors are a good option, particularly if your drives are installed what I call the bundus, you know, out in the farming areas, agricultural areas, the electricity isn't always the cleanest. So surge arrestors definitely in the outskirts areas. The drives do have built-in surge arrestors internally. Something I learned quite recently, if you do remove the EMI filters on the drives for whatever reason, that does disconnect the internal surge protection of the drive. So for instance, if you do need to remove the EMI filter in one of the drives for whatever reason, then definitely external surge is definitely advised, because you are basically disconnecting the internal surge protection when you remove that filter. Also, external surge is obviously preferred. It's a lot easier to change an external surge cartridge rather than having to send perhaps the drive in, because the internal surge took a knock and now it has to get repaired. So surge, yes. Outlying areas, I would say almost a definite. For your factories and your metropolitan areas, generally one surge in a main DB is enough. You don't need to have a surge on every single drive or every single panel that's in your factory. I hope that answers the question.
Okay. And then last one, is there a training course available that clients can attend? Obviously, once we're all allowed to travel again.
Yeah, this is a sore point. A lot of my life is around the training and our training agendas. We have training at EM all around the country. So if you log on to our website, you'll see there's a training link right at the top of the web page where you can register for VFD training. I think currently Durban, Joburg and Cape Town offer it, but as Conrad mentioned, unfortunately due to COVID, we have suspended all training. Very sad. I love giving the training. We have great facilities for it. We've designed and developed specific training rigs with drives, buttons. We've designed wonderful presentation notes as well. And it's a very interactive training. It's not sit on your chair and look at a slide. You physically have a drive, you have cables, you have switches in your hands. You must wire, you must program, and you must interact with the product. I can't wait for the training to get back up and running. I really do. Until then, we do things like this to make up for the losses. So please, guys, go ahead, register on the training or drop us an email if you want to do training. We can make special cases here and there, but obviously it's going to be case by case until we know exactly what's happening.
Great. Well, thank
Cool.
you. There we go, folks. First online, let's call it training, done for our clients. I hope you all enjoyed it. It was interesting for myself. Like I said, it was a first for me and for William. So
Yeah.
if you have any comments, please drop your relevant salesperson an email. Those who are interested in receiving the presentation, please let us know. Anita, I have marked your name down already, but if anybody else would like a copy of the presentation, please let us know and we'll get it through to you.
I've also recorded this presentation, so we can give you the actual file as well as the video link if you want to hear me talk again.
Yes.
Thank you, Conrad, for your lovely introduction, and thanks all who are viewing this. Really appreciate the time, and Conrad, the kind words.
Stay safe, everybody.
Cheers all.
Cheers.
Cheers, Conrad.